Yes. Now it's fine.
Okay. Oh, perfect. Now it's fine. All right. Okay, good. Okay, so let's carry on then. So let me share my screen then. Okay, now it's working. Fine. All right. Okay, thanks. All right. So, right. So what is the d derivative of a form? So we have a vector field x, and we have a k form omega. So then the Lie derivative of the k form omega with respect to the vector field x is again a k form Lx omega. So this is defined to be ddt at t equal to 0 of phi t star omega. So this is a k form. Okay. Where here phi t is the flow of x. All right, is the definition clear?
Yes.
Now, clearly, so we say that x preserves the vector field, preserves the form omega if phi t star omega is equal to omega for all t. So if this happens, then of course the Lie derivative is 0. Okay, but the converse is also true. If the Lie derivative is 0, then the flow will preserve the form. So the proof of the backward implication is that you look at ddt of phi t star omega. So this is dds at s equal to 0 of phi t plus s star omega. And now you use the fact that phi t is a flow, so phi t plus s is phi s composed with phi t, and pullback is contravariant. So phi t plus s star will be phi t star of phi s star. So when you substitute that here, you get dds at s equal to 0 of phi t star of phi s star of omega. And now pullback is linear. Phi t star, this t is fixed, s is varying. So phi t star is a fixed linear operator. So you can pull it out of the derivative, right? Because it's linear. So this will become phi t star of dds at s equal to 0 of phi s star omega. And what's inside is just the B bracket, right? So this becomes phi t star of Lx omega. And so if Lx omega is 0, then this pullback phi t star of Lx omega is 0. So that means that phi t star omega is constant. And so therefore it's equal to phi 0 star omega for all t, and phi 0 is the identity, so this is just omega. Is this clear?
Yes.
Okay. So the Lie derivative measures how much the flow preserves the form, okay? Or rather, how much it fails to preserve the form. It's zero if and only if the flow preserves the form. Okay. So, I mean, I can, as an example, you can use the Lie derivative to define the divergence, what's called the divergence of a vector field in Rn So here in Rn, you let dvol be the standard form which you integrate to get Euclidean volume or Lebesgue measure dx1 wedge dxn. So this is an n form on Rn. Okay. And so if I take any vector field x on Rn, okay, then Lx of dvol, this is also going to be an n form on Rn.
Yes.
Therefore, any n form on Rn is of the form some function h times dx1 wedge dxn, right? Yes.
Yes. Yes.
So you define this function to be the divergence of x. So div x is defined to be this function h. Okay. All right.
Yes.
So the flow phi t flow of x, this is volume preserving. Well, this will be if and only if Lx dvol is 0, right? By what we saw above. And this happens if and only if divergence of x is 0. Okay? Is this clear?
Yes, sir.
Yes. Sir.
All right. So the divergence measures how far the flow of a vector field is from being volume preserving. Okay. So we'll see the divergence again defined for a Riemannian manifold later in the course. But in Rn, it's easy to define this way. Okay. All right. And well, using Cartan's formula, which we'll prove again now, actually you can show that if x has coordinates x1 up to xn, then divergence x is summation I goes from 1 to n del capital Xi del little xi. Okay. So yeah, we'll prove this formula later. Okay, so now let me come to Cartan's formula. And so for this, we we're using the prism operator, right? So first we take a vector field X on our manifold M, and then we take phi t is the flow of X, and then we take the prism operator P associated to the flow. So PC of t comma little x is phi t of cx. Okay. And then we take the small prisms for epsilon small close to 0, p epsilon c of tx is pc of epsilon t x. Okay, so then we know for any form alpha, 1 over epsilon p epsilon. Well, okay, so let me first let me say okay, all right, so for any L form alpha and C and L minus 1 cube, we know that the integral of alpha over p epsilon c is equal to the integral of p epsilon star alpha over c, right? Yes, where p epsilon star was the dual operator on forms, right? Which sent
Yes.
L forms to L minus 1 forms. Okay, and 1 over epsilon p epsilon star alpha, this converges as epsilon goes to 0 to the interior contraction Ix alpha, right? We saw this. Yes?
Yes,
Okay.
sir.
Okay. So now let omega be a K form, and let C be a singular K cube. Yeah. So then we have this formula for the boundary of the K plus 1 cube. So this is 0, 1 to the K plus 1. And we have a K plus 1 cube P epsilon C. Okay. So that will be some cube like this. Okay. So the bottom is C itself. The top is phi epsilon composed with C. And the vertical sides, this is P epsilon of boundary C, right? Is this clear? Okay. Yes?
Yes.
Okay, so the boundary of P epsilon C is phi, the top minus the bottom. So phi epsilon composed with C minus the vertical sides. So that's minus P epsilon of boundary C. Okay. Now we integrate omega over this. Okay, so integral. So note that C is a K cube. So P epsilon C is a K plus 1 cube. So its boundary is a K chain again, right? All right. And similarly on the right hand side, phi epsilon composed with C is a K cube. C is a K cube. Boundary C is a K minus 1 cube. So P epsilon of boundary C is again a K chain. Okay. Sorry, boundary C is a K chain, K minus 1 chain. So P epsilon of boundary C is a K chain. Okay. So both sides are K chains. So we integrate omega over this. So integral omega over boundary P epsilon C is integral over phi epsilon composed with C omega minus integral over C omega minus integral over P epsilon P epsilon boundary C of omega. Okay. Now for the first term, we can use Stokes' theorem. This is the integral over P epsilon C of d omega by Stokes' theorem, right?
Yes.
Yes.
And this term, by definition, this is what? This is the integral over 0,1 to the k of phi epsilon composed C star of omega, right? So phi epsilon composed C star of omega minus integral over C of omega. Okay. Minus for the last term, we know that integral omega over P epsilon of some chain is the same as the integral over boundary over that chain of P epsilon star of omega, right? Yes?
Yes, sir.
Yes.
Okay, and now over here, I can again use that the integral of d omega over P epsilon C is the same as the integral over C of P epsilon star of d omega. Okay, and here phi epsilon composed C star of omega is the same as C star of phi epsilon star of omega over 0,1 to the k, right?
Yes. Yes.
Okay, minus integral omega over C. And here I can use Stokes' theorem again. This is minus the integral over the boundary is the same as integral of d of this form P epsilon star omega. Okay. Yeah, by Stokes' theorem. Yes.
Yes.
Okay. Fine. So now this is integral over C P epsilon star d omega, and the integral over 0 1 to the k of C star of some form is basically by definition the integral over C of that form phi epsilon star omega, right? Yes.
Yes, sir.
Yes.
So I can take this omega together with this, right? Okay. Yeah. And then I have minus, so all become integrals over C. So I have minus d of t epsilon star omega. Okay. So now all I do is I divide everything by epsilon, right? I divide all the terms by epsilon. Okay. Okay, divide everything by epsilon. So now what do I get? Inside I'll get this 1 over epsilon p epsilon star. Here I'll get phi epsilon star omega minus omega divided by epsilon. And here I'll get 1 over epsilon p epsilon star, right? Yes?
Yes, sir.
Now we know that 1 over epsilon p epsilon star applied to any form that converges to Ix of the form, right? The interior contraction. So therefore, this term converges to the integral over C of Ix d omega, right? Yes?
Yes.
Yes, sir.
Okay. And this phi epsilon star omega minus omega divided by epsilon, by definition, this converges to the Lie derivative Lx omega. So this term converges to the integral over C of Lx omega minus d of, so this term inside 1 over epsilon p epsilon star omega, that converges to Ix omega, right? So this becomes minus d of Ix omega. All right. So now this is true for all singular k cubes C. So we know that two forms are equal if and only if their integrals over all singular k cubes are equal, right? Yeah.
Yes.
So therefore, this implies that Ix d omega is equal to Lx omega minus d of Ix omega. Okay, so this is Cartan's formula if you take this dix omega to the other side. Okay. So this is sometimes called this Cartan's formula an infinitesimal homotopy formula. Okay, does this make sense? Because this term is what you get when you integrate over the boundary of the parallelogram, a boundary of the prism. This is coming from the boundary of the prism. This term is coming from the top minus bottom of the prism. And this term is coming from the vertical sides of the prism. Is this all right?
Yes, sir.
So this is a geometric proof of Cartan's homotopy formula for the Lie derivative. Okay. Yeah, I mean, in many books, you'll find this done in a purely algebraic way, which at least to me, I can't understand anything. When it's done purely algebraic, you just use properties, algebraic properties of the Lie derivative and the interior contraction and the exterior derivative, and somehow you prove it by induction. I mean, it doesn't tell you anything about what's happening, you know. So this it's a very easy proof, and you can see the proof literally. It's just the fact that the boundary of the prism is the top minus the bottom minus the vertical sides, minus the prism of the boundary. That's all. So, all right. Okay.
Yes.
So we have this formula for the Lie derivative. Lx omega is Ix d omega plus d of Ix omega. So example, if omega is equal to d vol, which is dx1 wedge dxm in Rn, okay, then what happens to this formula? Well, d omega is 0 because it's an n+1 form, right? On Rn. So therefore it's 0. Right? So therefore, Lx d vol is just d of Ix d vol. Okay? Is this clear?
Yes, sir.
And using this, you can prove the formula which I stated here, that the divergence is summation del capital Xi del little xi. All right? Is it clear? Yeah?
Yes, sir.
You use the fact that the Lie derivative is equal to d of Ix d vol, and then it's just a computation. We did this in our multivariable calculus course. If you remember, we actually did this. This was one of the exercises I said. I don't know if you remember, Orkojit Utsav. We did this problem in our multivariable calculus course. So, okay. All right. So that's about the Lie derivative. So the last topic in this first part is about integration on manifolds. So integration of top degree forms. Okay. Okay, so in an n-dimensional manifold, I mean, one forms you integrate over curves, two forms you integrate over two cubes, which are surfaces in the manifold, and so on. So an n-dimensional form in a n-dimensional manifold, one should imagine we should be able to integrate that over the whole manifold, right? So, so how do we want to integrate? So suppose, whatever, this is our manifold M. Okay. And what we want to do is to first reduce the integral of a global form into the integral of locally supported forms. So forms which are supported in charts. Because once I have a form in a chart, then I should be able to reduce the integral to an integral over some open set in Rn, right? Okay. So, suppose I have a form which is whose support is compact and contained inside a chart. Okay. So say this is a chart U. So suppose I have phi equal to x1 to xn, a chart. And I take a n-dimensional form such that the support of omega is a compact subset of U. All right. Okay. So this is the support. All right. So then what can I try to do? Well, using my chart phi, I can, with respect to the coordinates x1 to xn, I can write omega as h composed with the function phi, or let me write it as x. So dx1 wedge dxn, okay, where h is a smooth function with compact support in phi of u, right? I can write omega like this, yes?
Yes, sir.
Okay. So then it makes, we want to define the integral of omega over the manifold M then to be just the integral over phi of u of h dx1 dxn, right? Okay. So we're almost out of time. Let me stop this session and we'll start a new session. Okay. Okay. So okay. So we have this situation. We have a form omega whose support is contained inside a chart U. And with respect to the chart x, omega becomes some function h of x into dx1 wedge dxn, where h is a function, a smooth function with compact support in the image of u, inside phi of u, right? And so then we want to define the integral of omega over n to be the integral over phi of u h dx1 dxn. Now I ask you, what is the problem with this definition?
If we
What-
take another chart, then we have to have the consistency.
Okay, so this should be independent of the choice of chart, right? So let's take another chart then. Okay. Say psi. Such that the support of omega is also contained in the chart V. Okay. So say psi is a chart Y1 to Yn. Okay. And support of omega is a compact subset of V also. Okay. So then note that the support of omega is a compact subset of U intersect V. Okay. So this would be, say, the image of U intersect V under phi, and this would be the image of U intersect V under psi. Okay. So here we have the change of charts map. So this would be the change of charts. Let me call it F. So Y becomes F of X. Okay. This goes from phi of U intersect V to psi of U intersect V. Right? Okay. Yes.
Yes, sir.
Okay. So, what happens if I try to do this with the other chart? So psi is what? Psi is F composed with phi, right? Okay. So suppose omega is equal to G composed with Y into dy1 wedge dyn, right? Okay. So then that means that this is equal to psi star of the form G dy1 wedge dyn on Rn, right? Okay. So this is equal to phi star of F star of G dy1 wedge dyn, right? Yes. Okay.
So G is the coefficient with respect to this other coordinate. Right?
Yeah. So G will be a function with compact support in psi of V, right?
Yes.
Okay. So G is a function here and H is a function here. Okay. Right. So now this becomes what? This becomes phi star of G composed with F, and then F star of dy1 wedge dyn. We know what this is equal to. This
Okay.
is equal to the determinant of df into dx1 wedge dxn. Right? And
Yes.
on the other hand, we also know that omega is also equal to phi star of h dx1 wedge dxn, right? Okay. So if you equate these two, what do we get? We get that h dx1 wedge dxn is equal to G composed with F det df dx1 wedge dxn, right? Okay. So now if we use, so we want, therefore, the integral over phi of u h dx1 dxn to be the same as the integral over psi of v g dy1 dyn, right? Yeah, the left hand side is the definition of the integral if I use the chart phi. The right hand side is the definition of the integral if I use the chart psi, right? Okay.
Yes.
Now, what are these left hand side and right hand side? So H actually has compact support inside phi of u intersect v, right? And G actually has compact support inside psi of u intersect v. So therefore, these integrals are the same as the integrals over phi of u intersect v h dx1 dxn, and this is the integral over psi of u intersect v g dy1 dyn. Okay. And now in the right hand side, I can make well, let me look at the left hand side first, right? This H is actually equal to what? G composed F into det df, right? So this left hand side becomes the integral over phi of u intersect v G composed F det df dx1 dxn, right? Okay. Now, what about the right hand side? Well, the right hand side, note that F is a diffeomorphism the change of charts F. This is a diffeomorphism from phi of U intersect V to psi of U intersect V, right? Yes. So therefore, by the change of variables formula, you put y equal to f of x here. By the change of variables formula, what will this become? This will become the integral over phi of U intersect V, G composed F, into mod of det df, right?
Yes.
dx1 dxn. Yes, this is the change of variables formula.
Yes.
So now can you see what the problem is?
Yes. Yes.
What do you need? What do you need for these two to be equal?
Must have determinant df positive.
Right. So what we want, so thus we want determinant of d of, so f was the change of charts. F was psi composed with phi inverse, this change of charts. We want this to be positive for all charts, right? Or at least we want to choose our charts in such a way that this happens. Then the two integrals defined using the two charts will be equal. Is this clear?
Yes, sir.
Yes, sir.
Okay, so this leads us to understanding that we need a certain extra hypothesis on our manifold. So what we want, therefore, an atlas of charts phi I on M such that the determinant of D of phi I composed phi j inverse, this is positive for all ij. Is this clear?
Yes, sir.
So this condition A may not always hold, but this is an extra hypothesis that we are putting on our manifold. Okay, so we will say, well, this is one definition. M, so there exists such an atlas. M is orientable if this condition A holds. So there are different definitions of orientability which are equivalent. This is one definition. This is motivated by wanting to define the integrals of forms in an unambiguous way. Is this clear?
Yes.
Yes, sir.
Okay. So we want our changes of charts to be orientation preserving diffeomorphisms from Rn to itself, right? The changes of charts are orientation preserving. That means their determinant, the determinant of their derivative is positive everywhere. Okay. So what is the more, let's say, topological definition of orientability? That is the following, and this is really a Well, it's not purely topological, but you can give a purely topological definition of orientability even for topological manifolds, not necessarily smooth. So topological definition of orientability is the following. So first, we define what is an orientation on M. Okay. So an orientation on M is a choice, so is an assignment P in M goes to mu P. So mu P is what? Mu P is an orientation on TPM. Okay. So this OR of TPM, this is the set of orientations on the vector space TPM. Remember, we defined what is an orientation of a finite dimensional vector space. It was an equivalence class of ordered bases, right? Yes?
Yes, sir.
Yes.
So this, remember, this was in one-to-one correspondence with the connected components of GLV. If V is your vector space, finite dimensional vector space, then GLV has two connected components, right? And GLV acts on the set of ordered bases simply transitively, right? So the orbit map is a bijection for any point in the set of ordered bases. So you can identify the set of ordered bases topologically with the space GLV, and GLV has two connected components. Those correspond to the two possible orientations on V, right? You remember this?
Yes.
Okay. So what is an orientation on a manifold M? That means we have to choose for each point P an orientation on the tangent space, all right? But now be careful. We want this choice to be continuous in the following sense. So which is continuous so you see let me try and explain what this continuity means. So I'm just going to write this in. Okay, let me just give the definition and then I'll explain it. So if for any chart U phi, yeah. So, well, I should say for any connected chart. Usually charts we take, I mean, they're homeomorphic to balls usually, but just to be extra precise, I'll say for any connected chart U comma phi, we have either, so if I have a chart, then for any point P in the chart, I have my orientation mu P on TPM, and I have the derivative d phi at P. That is an isomorphism from TPM to Rn. So if I have an isomorphism between finite dimensional vector spaces, I can use it to push forward orientations on one vector space to the other vector space, right?
Yes.
Right. So what we want is that d phi p. So push forward is always lower star. D phi p lower star of mu p. Either this is equal to the standard orientation. So let me call this nu naught equal to standard orientation on Rn. So this I want to hold for all p in U, all right? Or the opposite holds, that d phi p star of mu p is equal to nu naught op, which is the opposite of the standard orientation on Rn. This I want to hold for all p in U. Okay, so one of these two holds. Okay, so it cannot be that at some point in my chart, I push forward to the standard orientation, and at some other point, I push forward to the opposite orientation. That cannot hold. All right? Is it clear?
Yes, sir.
So actually what is happening is, now let me explain what the picture is. So if this is M, okay, then for each point P and M, I have, you can think of the set orientations of TPM. So that's a 2-point set. So I have these 2 points sitting above P, all right? And now as P varies, I get, for each point, I'll get 2 points above, right? Yes? Okay.
Yes.
Yes.
So this set above, this is, let me call this or of Tm. So this set comes with a projection to M such that the inverse image of any point is 2 points, all right? And locally, this is a product. So this is what is called a fiber bundle. Okay, this is a fiber bundle over M. This is a fiber bundle over M. So if this projection is pi, so in this case, cardinality of pi inverse P is 2 for all P. Okay. And an orientation on M, what is this in the language of bundles? It will be a, so when you have a bundle, you can look at some objects associated to the bundle, right? What will an orientation be for each point P? I'm choosing a point in the fiber. What is such an object called? What is such an object called? It's a section, exactly, yes. So this continuity means this is a continuous section, is a continuous section. It is a continuous section of this fiber bundle. Okay, so the key point is continuity. You see, what I don't want is to be choosing points like this and suddenly I jump, you know, and then I choose points above here. You understand? Right? I don't want any jumps. My choice has to be continuous. Okay? So, does this make sense?
Yes.
Yes, sir.
Okay. So, this may not always be possible. So, I mean, what is an example of a fiber bundle like this? You already know such an example. You take the map, Z goes to Z squared from C star to C star. So you know this from your complex analysis. So a covering is a fiber bundle actually. Any covering is a fiber bundle where the fibers are finite. So in fact, this is a covering. This is a covering. This is in fact a covering. So anyway, so Z goes to Z squared. Here the fibers, so if this is your map pi, so here every point W has two pre-images, right? So here can you choose a continuous section for this fiber bundle? So here you have for every point in the range, you have two pre-images, right? Two square roots. You have two square roots, which are negatives of each other. Can you choose a section here? Yes. Do you have a section, a continuous section? What is your answer? Yes. Is there a section?
I mean, if we keep on choosing from one half plane, won't that help?
Well, can you? What is your answer? Yes or no? Do you have a section in this case? Any guess? What do you think? Yes, no?
I think no, but I wonder why.
We have to take
Yeah,
a branch like along or something.
the answer is no. There is no section of this. There is no continuous section everywhere.
Because of that things are that in the negative real axis kind of a thing, when we go from this side to that side, continuity is lost, like this sort of.
Well, think about this. Suppose I had a section, right? Yeah, so I have my map pi. Yes. Suppose I had a section.
Yes.
Let me restrict it to a circle passing through, say, the unit circle. Let me restrict my section to the unit circle, right? Yes.
Yes. Yes.
Yes, sir.
Then I would have a choice of square root along this curve. But I know the unit circle, I can think of this as a loop, right? Now, any loop, it lifts because this is a covering map. It lifts to the cover, right?
Yes. Yes. Yes.
But
Either
my
it will
covering
be
space-
infinite or it will be a loop.
But in my covering space, I know that my lift goes from one square root to the other square root, right?
Right. Right. Yes.
And that's a contradiction because the image of this connected set should, well, I mean, the image of, well, the image of a loop will be a loop, right? This is not a loop. That's it. So, okay. If I had a section, the image of this loop would be a loop, right? But the image is not a loop because the image is the lift, right? And the lift I know goes from one square root z to the other square root minus z. Is this clear?
Yes.
It's just
Yes,
covering theory. You know there's a unique lift. You know there's a unique lift of any loop, right? So, and that's it. So, okay. Okay, so not every fiber bundle has a continuous section. Okay, so this is, you can see this is becoming more topological, right? It's almost purely topological. The only thing is, well, this TPM, we're using the smooth structure here, and this D-phi, we're using the smooth structure. But actually, if you do, I mean, in algebraic topology, what happens is your orientation is you look at basically the relative homology Hn of the manifold with respect to manifold minus the point P. Sorry, not cohomology, homology. Yeah, maybe you did this with Shomik in your algebraic topology class, right? So you look at this with Z2 coefficients. You look at this with Z2 coefficients. And this is, because M is a manifold, this is isomorphic to Z mod 2. Right, by excision, this is the same as ball and ball minus a point. And for ball, you know, this is from the long exact sequence, you'll get that this is Z mod 2, right?
Yes, sir.
Okay. So this is your, so this is a purely topological object, right? This you can define for a topological manifold. So you don't actually need a smooth structure, you see? So this will be the fiber, this will be the fiber over P. Do you understand? This is your 2-point set which maps to P.
Yes.
And you can glue all of these together to get your fiber bundle. So you can define it in a purely topological way. Does it make sense now? Yeah?
Yes.
Yes, sir.
Okay, so orientability actually is a purely topological concept. You don't need a smooth structure. It's a purely topological concept, but we are using the smooth structure to make things easier. Okay. Is this all right? Yeah. Okay. So, so definition B is that M is orientable. So B is M admits an orientation. Okay, there exists an well, let me write it this way. B is there exists an orientation on M. Okay, and then it's not hard to show that A is equivalent to B. Okay. So let me just, I won't write this. I'll just talk you through the proof of this. So see, suppose you have an atlas so that the change of charts is orientation preserving. Then how do you get an orientation on M? Anyone? Orkojit Utsav, how will you get your orientation on M? So you have this nice atlas. Using this atlas, I want to construct an orientation. What do I do?
So I assign this.
I mean, we can push forward the orientations from the.
I use this atlas. I just pull back the orientation on Rn, the standard orientation on Rn,
Yes,
in my charts, right?
that's
Now,
it.
this is well defined because the change of charts is orientation preserving, right? So the change of charts takes the standard orientation on Rn to the standard orientation on Rn. So it doesn't matter which chart I pull back by, because they differ by an orientation preserving map of Rn, right? Is that clear?
Yes, yes.
Okay, so I can just pull back by this good chart. So this is called an oriented atlas, by this oriented atlas. And I'll get an orientation on M, right? And now, similarly, how do I go in the other direction? So suppose I have an orientation on M, then I want to define such an atlas, right? Okay. So now I take any atlas, right? Now, without loss of generality, I can assume that, let's say, all the elements in my atlas, right? They're all the charts in my atlas are connected. Okay, fine. So then, sorry. Yeah, so suppose I'm given an orientation, I want a good atlas. So what do I do? Well, I know this continuity property holds for my charts, right? So what happens? Either for my chart, either the given orientation mu p, it maps to the standard orientation for all p, or it goes to the opposite orientation. So if it maps to the standard orientation, I keep that chart in my atlas. If it goes to the opposite orientation, what I do is I simply compose my chart with an orientation reversing map of Rn to Rn. For example, a reflection, right, in a hyperplane. I just compose with one reflection of Rn, right? And that becomes a new chart, which then sends the given orientation to the standard orientation. Is it clear? Then I
Yes,
take
sir.
that new chart. Okay, so now I get new charts, and then they satisfy the compatibility condition. The change of charts is orientation preserving. Is this clear?
Yes, sir.
Okay. And both of these are equivalent to a third property, C. There exists omega, a top degree form, an n form, such that omega p is non-zero for all p. Okay, remember, this means that on each tangent space, we have a non-zero top degree form. And so that defined an orientation, right? Right? We did this when we were talking about orientations on a finite dimensional vector space.
Yes, sir.
Okay, so this will give you an orientation on each tangent space. All right. Okay. So let me stop this session. We're out of time, and we'll start another session. Okay. Okay, so orientation is orientability. There are three equivalent definitions. Okay, all these three are equivalent. Okay, you can try to prove the equivalence of C with either B or A as an exercise. All right. Okay. Yes, is it all right?
Okay.
Yes.
Okay. Yeah, it's a good exercise to prove that C is equivalent, for example, to A. Yeah, it's easier to prove that C is equivalent to A. You just, A and B you already know are equivalent. So just prove that C is equivalent to A. Okay. Okay, and special case, if M is equal to sigma, which is a surface in R3, okay, so for example, it could be, I don't know, a torus sitting inside R3. In this case, what happens is that you have another equivalent condition for orientability, which is that there exists. So at each point, so the tangent space is two-dimensional in R3. So the orthogonal complement is one-dimensional. So there are two, at each point, there are two unit normal vectors, right? So I have a choice of two unit normal vectors. And what I want is that there exists a continuous unit normal, there exists a continuous unit normal vector field on sigma. Okay, so D is equivalent to orientability also. D is equivalent to whatever, ABC.
ঠিক আছে বলবো। হুম? বুদ্ধি ঠিক আছে। মোটামুটি আছে, শুনতে খারাপ বলছে। কি হয়েছে?
All right. So how do you see this? So you have a normal vector field. So you call it N from sigma to R3, right? Well, actually, N will go from sigma to S2. It's a normal, a unit vector at each point, a continuous normal vector field. Then if you have N, you just define, so given N from sigma to S2 such that NP is perpendicular to TP sigma for all P. You define mu P to be the equivalence class of any basis VW, ordered basis VW, is an ordered basis of TP sigma such that N comma VW is equal to the standard orientation nu naught on R3. Does this make sense? Yeah.
Yes, sir.
NP. Yeah, NP VW is the standard orientation on R3. Okay, you can check that this is a well-defined orientation on TP sigma, and this will define an orientation on sigma. All right. Okay.
Yes.
Right. So yeah. So you choose VW here so that the three of these, the triple N VW, becomes gives you the standard orientation on R3. Okay. So this gives you an example of this leads to an example of a non-orientable surface, which is the Mobius strip. This is non-orientable. And I won't give a rigorous, but the point is because basically what happens is here because of the twist, if I start out with one normal vector like this, so by continuity, as I move along the Mobius strip, okay, my normal vector has to point like this. And because I'm twisting it, what will happen is in the end, the normal vector will point in the opposite direction. Right? So the normal vector will have a discontinuity. You can't get a continuous normal vector field. All right. The Mobius strip has only one side, right? If you put your finger on one side, that will determine a normal vector, right? But as you move your finger along the Mobius strip, you come back to the other side, right? Yes?
Yes.
Other
Yes,
side,
sir.
what you started. So that means the normal vector will flip and you'll come back to the opposite normal vector. So you don't have a continuous normal vector field. All right. So, okay. So just to give you example of a non-orientable manifold. All right. Yeah. Okay. Also, RP2 is also non-orientable, but I'll have to think about a proof for that. Yeah. So anyway, okay. So fine. So good. Good. So we have orientability. So now it should be clear now that given an oriented manifold, so that means a manifold together with an orientation, which is the same as given an atlas of a good atlas of compatible charts, right? Yeah. So that means so let me take the definition using charts. So given charts phi I, ui, such that determinant d phi I phi j inverse is positive for all ij. Now we can define the integral of omega over m, the integral over phi of u, h dx1 dxn, okay, if omega is an n form such that support of omega is a compact subset of u, and omega is equal to h composed with x into dx1 wedge dxn on u, where h belongs to cc infinity phi of u, and u phi belongs to our oriented atlas. Okay. Is this clear?
Yes.
Yes.
Okay, so this is well defined now. Now this is well defined, right? Yes, because the determinant of the change of charts is positive. So this is well defined. All right. Okay, so on an oriented manifold, we can define the integral of a smooth form with compact, an n form with compact support inside a chart. All right. Okay. And now for a general, okay, so we also define the integral of mod omega over m to be the integral of mod h dx1 dxn. So this is an L1 norm of my form actually. This is sort of an L1 norm. Okay. So we define this because I want to define for a non-compact manifold what are integrable forms, integrable n forms. And now, so definition. So omega is an n form on M. M is an oriented manifold now. So that means a manifold equipped with an orientation or equivalently with an oriented atlas. Okay. And so then what we do is, so if UI are charts of an oriented atlas. Okay. So then you let phi I, so these are going to be smooth with compact support in UI. Let this be a partition of unity subordinate to the cover UI. Well, actually, yeah, you don't need, well, okay. A partition of unity subordinate to UI. Okay. So then phi I times omega. So then omega is equal to so yeah, so this UI is a locally finite. I assume that UI is a locally finite covering. I need this for a partition of unity. This is a locally finite covering of M. So then omega I can write as summation phi I times omega. And phi I times omega, the support of that is contained inside UI. So for this, the integral is well defined, right? So first of all, we say that omega is integrable if the sum over I and I integral of over M of mod of phi I omega, this is finite. Okay. And for an integrable omega, we define the integral of omega over M to be the sum over I and I integral over M of phi I times omega. Okay. Is this all right?
Yes.
Yes, sir.
Oh. So that defines integral of a n form over an oriented manifold, right? So the point is we do need an orientation in order to define global integrals. We do need an orientation on the manifold. Okay. All right. Good. So the last topic that we need to get to briefly is Stokes' theorem for manifolds with boundary. Okay. Fine. So, well, let me just at least start that. So, oh, so one, yeah, comment here. A fact. This integral omega over n. This is well defined, independent of the choice of cover and partition of unity. Okay. All right. So if I choose a different cover partition of unity, it will give me the same answer. All right. Okay. So, all right. So this defines the integral of an n form over a manifold, and also, so this is one fact, and also if M is compact, then all omega, which are you just actually need omega to be a continuous form, not even smooth. All omega will be integrable. Okay. Yeah, because then, I mean, you can just a finite cover. And so, okay.
Yes.
All right, fine. Okay, good. So now we want to come to manifolds with boundary. Okay. Okay. So any questions? Any questions? Yeah. Okay. So you know what intuitively what a manifold with boundary looks like, right? It could be, for example, a torus minus a disk, right? So the boundary would consist of this circle here, right? This would be the boundary of the manifold. So the point is, I mean, for points which are not in the boundary, these have a neighborhood which is homeomorphic to a disk in R2, whereas for a point on boundary, you get a neighborhood which is homeomorphic to a half disk. Right? So,
There's a half space, yeah.
right. So now what we want to do is we define the half space, the closed half space. There's some disturbance coming. What is? Yeah. Okay. So we define the closed half space. H upper n to be X in Rn, where the last coordinate xn is greater than or equal to 0. Okay. Fine. Then we have the following definition. Oh, wait. So before that, yeah, I want to say that. Okay, so. Yeah, so we say that a map um, F or say, yeah, F from an open subset of the closed half space into, say, some Rm is C infinity if so for all P in V, well, if P belongs to the interior of Hn, then F is just C infinity in a neighborhood of P in Hn, neighborhood of P, well, in Rn, then. Okay. Whereas if P belongs to the boundary of Hn, then what we want is there exists U neighborhood of P in Rn, and there exists a C infinity map F tilde from U in Rn to Rm. So U is open here. Okay. Such that this is an extension of F. So F tilde restricted to U intersect V is equal to F restricted to U intersect V. All right. So locally you extend to a smooth function in a neighborhood. Okay, so here is P on the boundary of the half space, and whatever, this could be your open set V. So this is V, which is open in Hn, and here I want a neighborhood U such that I have an F tilde here, right? And over here, F tilde is equal to F. Is this all right? Yes?
Yes.
Okay. So you have a smooth extension. You have a smooth extension. So once you do this, then you can define any partial derivative. Note, if I take any partial derivative, so of order k, so del k, del x I1, del x ik, So rather, how should I say this? So yeah, so then you define the partial derivatives of f at p to be the partial derivative of f tilde at p. Okay, and this is well defined because this is equal to, since f tilde is c infinity, so the partial derivatives are continuous. So this is the same as the limit q tends to p, q belongs to the interior of Hn, del k f tilde del x I1 del x ik of p, and this is equal to the limit q tends to p, q belongs to interior of Hn, del k f del xi1 del xik. Oh, sorry, this p should be a q here. This should be q. Okay, so this last limit is independent of the choice of f tilde. Is this clear?
Yes.
Yes, sir.
F tilde is equal to f in the interior of Hn. So you can replace the f tilde by f here. And so this is independent of the choice of f tilde. Okay, so the partial derivatives of f make sense at boundary points. All right. Okay. And so then we can now define what is a manifold with boundary. So okay, so to save time, let me now go to the notes because the definition is given there. So we've done this. So let me switch to the notes. So right. Okay, so we have manifolds with boundary. Right. So manifold with boundary is like a manifold. It's a second countable Hausdorff space M together with the family Ui phi I, such that Ui is an open cover of M. And for all I in I, phi I goes from Ui, which is an open subset of M, to Vi, which is a subset of Rn. This is a homeomorphism where Vi, though, is either an open subset of Rn or an open subset of Hn. Okay, so like in the picture here, the image of the chart, this here your V is an open in Rn, and here this V is open in Hn. Is this all right? Okay.
Yes.
Fine. Yeah. And what we want is that the change of charts now, okay. So the change of charts, this goes from an open subset of Vi, phi I of Ui intersect Uj. This goes from Vi to Rn. This we want to be smooth. So here, Vi could be an open subset of Rn, in which case this is just a smooth map from Rn to Rn, the usual definition. Or Vi could be an open subset of Hn. In that case, the definition is of smooth is the definition that we've given here. All right. Is it clear? That near each point you have an extension to a smooth function in the lower half plane as well. All right. Is it clear?
Yes, sir.
Yes.
So the definition of, yes. So the change of chart should be smooth in this sense. Okay. All right. And okay. So now we say that P, a point of M, is a boundary point of M if phi of P belongs to the boundary of Hn for some chart phi near P. Okay, so M is manifold with boundary. Okay. And so we say that P in M, this is a boundary point if phi P belongs to boundary Hn for some chart phi. In that case, in fact, phi of P belong for any chart psi psi of P will also have to belong to boundary Hn. So how do you see this? So you have your point P, right? And we're taking some neighborhood of it. So the neighborhood really will look like this. Okay. So under phi, I know that this maps to a boundary point of Hn. Okay, this is phi of P. And so to prove that this happens for any other chart, suppose not. Okay. So then I have some chart psi such that this maps into Hn, or right to an open subset in Rn. Okay, this would be psi of P. Okay. Now you look at the change of charts this way. So you look at F equal to phi composed with psi inverse. So now this is a continuous one-to-one mapping. Yes?
Yes, sir.
On an open subset of Rn. Because I'm assuming that psi maps a neighborhood of P to an open set in Rn. Okay. But then this implies by Brouwer's, so this is a deep theorem, by Brouwer's invariance of domain, F is an open mapping. Right? Okay. But if F is an open mapping, then the image of this neighborhood of psi of P, that will be a neighborhood of phi of P inside Rn, right? So then the image of F will intersect the lower half space. But that's a contradiction. Is it clear?
Yes.
Okay, so that means image F intersects H and complement. So that's the contradiction. Okay, so yeah, that basically says that the boundary points of a manifold with boundary are well defined. Those are the points which map under any chart into the points of boundary Hn. Is it clear?
Yes.
Okay, so right, so we have less than a minute, so I guess we can stop here. All right. Then we'll finish talking about integration on manifolds with boundary and Stokes theorem next time. Okay.
Okay.
So, okay. All right. Thank you. So let's stop here.